Now, in this video, I'll be talking about LED, light emitting diode. All right, so this is one of the applications of PN junction where we exploit the junction and and we have the output in the form of light. Now, to start with this, I would call this LED as a specially heavily doped PN junction. So it's a heavily doped. It's a heavily doped PN junction. And which emits spontaneous radiation when forward biased. So when we forward bias a PN junction which is heavily doped and is specially designed, then it emits spontaneously radiations in the forward biasing mode, and this device is called as light emitting diode. So light emitting diode basically converts, it converts what? Electrical energy into light energy. We can also say electromagnetic energy. Okay, so the symbol in this case, we have a PN junction, it's forward biased, and we have light coming from it. Now, so this is the symbolic presentation of a light emitting diode. Now, talking about the elements like silicon and germanium, I mean, LEDs made of these semiconductors, they emit energy in the form of infrared radiations. So infrared or heat radiations, right? Okay, so so we make use of some special compound semiconductors, and the examples of these semiconductors are gallium arsenide is there, and we have to be precise in materializing a semiconductor like gallium, arsenic, and phosphorus. So you have to have the right combination of the elements present in the crystalline network, where we can have the radiation that's being emitted by this PN junction that should fall in visible spectrum. Now, to move on from here is like, so this is the symbolic presentation of a PN junction, a specially designed PN junction which emits light radiations when we forward bias this PN junction. So in moving forward, if I talk about this the LEDs that we have made of gallium, say for example gallium arsenide, they have the band gap, the energy gap. They have the energy gap Eg. This is nearly equal to 1.4 electron volts. And if we take more precise elemental composition of this gallium arsenide and add some phosphorus on it, we will have Ga As 0.6 and phosphorus 0.4. Now here we can see that the band gap is nearly 1.9 electron volts. Now this energy is again suitable for infrared. So you're going to get the heat from this compound, but when you add phosphorus in right proportion, you have the band gap of 1.9 electron volts, and in this case it will emit red light. So this is how we should understand the sensitivity of the proportion that's being used while preparing a compound semiconductor. And research is ongoing in this field in current times, where people are trying to look for new materials where we can have the tuned energy bands. Now, if I have to explain this concept, we have a PN junction, and this is a forward biased PN junction. So this must be positive, this must be negative, and what happens is you give the current and you develop electron, and you just have these electron hole pairs, and they emit radiation. Tuned, so their band gaps have to be tuned, right? So when you tune down these PN junctions, you have the visible light, right? You have the visible light. Now, to understand the theory of this light emitting diode is when this PN junction diode is forward biased, the electrons ejected to the p side. So it has a p side and it has an n side. Now these electrons which are ejected into the p side of the junction diode, they fall from the conduction band to the valence band and recombine, and they recombine. So you have an energy band gap here, a kind of band gap where you have electrons here, they will be jumped here. So what's going on here? You have a hole here and you have an electron. So you have developed an electron hole pair, right? So what happens is this is equivalent to the jumping of electron from higher energy state to the lower energy state, right? So hence energy is released in this process. Now once these electrons jump from say valence band to conduction band, you have the release of energy, right? And hence this energy is released in the process of recombination. When they will recombine, when this electron will come back to the valence band, it will emit the radiation, right? So that radiation comes out. Now this the process of giving light by applying the electrical source that we have applied here, an electric source of energy, it's also known as electroluminescence, right? It's also known as electroluminescence, right? So electron getting excited from the valence band to the conduction band, then recombining spontaneously to its valence band hole. So this process constitutes the emission of energy, and this phenomenon is also known as electroluminescence. Now, the energy of the photon of the visible light is given by Max Planck's equation, E is equal to h nu, right? And we can immediately convert this equation in terms of wavelength. So E will be equal to h nu by c, where nu is c by lambda. So this is the relation between the frequency and wavelength of light. So this is h nu. This is h nu here, sorry. So this has to be h c by lambda, right? So E is h c by lambda. So we can also have the wavelength. We can calculate the wavelength, and that wavelength will be hc upon energy gap. Now this E will refer to energy gap in this case, in this situation. So if we simplify this hc, we can write down in the short form here that this lambda, this lambda is 1242 electron volt into 10 to the power of minus 9 divided by the band gap. Okay, so we can calculate lambda here. So this is 1242 nanometer electron volts divided by band gap. Now from this equation, if we know the energy gap of this PN junction, we can calculate the wavelength of the light that's emitted by this light emitting diode. So talking about the VI characteristics, they are same as that of elemental semiconductors, say silicon. There is knee voltage. So all these things are absolutely in the same domain. And now talking about the advantages of these LEDs. These LEDs, what we have LED, we have positive, negative, and we have energy in the form of light. Okay, so it's a PN junction. Fine. Now these light emitting diodes they can be easily manufactured, so cost is less. That should be the point number one. And point number two should be that these LEDs they work at low voltages. So you don't need a lot of voltage for them, right? As compared to the incandescent bulbs that we used to have in past. I remember the bulbs having those filaments. They are still in use, but not much. This LED has longer life. Certainly, the bulbs we used to buy are made of those incandescent resistors. Their lifetime used to be very small, but these light emitting diode based bulbs, they have longer life in comparison to the incandescent bulbs. They can be switched on and off very fast, so they can be used as blinkers. Okay, so we can use them as blinkers, blinking of eye. So there is no warm-up time. They don't take time to warm up. They consume very less power as compared to the incandescent bulb that I talked about. Now, these are the advantages of these light emitting diodes, and they can emit monochromatic light as well as white light. So monochromatic means they can emit the light of single wavelength, the light of single frequency. So these were the advantages. And talking about their uses, as I talked about their advantages. These advantages are taking these light emitting diodes, making them very useful in day-to-day problems and day-to-day technology that we have. And to proceed from here, I mean, they can be used as indicator lamps. Okay, they are used in digital displays that we see. These light emitting diodes, which emit infrared light, they are used in burglar alarms. That you will have an alarm. You might have watched those movies where somebody having some interaction with some kind of radiation and there is an alarm. They are used in remote control schemes. They are used as blinkers. They are used to decorate the lights. They are used as night lamps and in torch. All of these things are the applications of these light emitting diodes. And at the same time, if we talk about the spectral range of visible light. Now, what is the spectral range? Spectral range of visible light. Okay, so how much is that? That's nearly 400 nanometer to 700 nanometer. So all the wavelengths that fall in this range, they fall in the visible portion of electromagnetic spectrum. Now, if we convert this wavelength into energy, it is from 1.8 electron volts to nearly. No, sorry, I'm going in the reverse. It's nearly 3 electron volt to 1.8 electron volts. So this will be the range of energy gaps that you will need to have the wavelengths between 400 nanometers and 700 nanometers, right? So this will certainly enclose the VIBGYOR, right? And I think everybody is aware about VIBGYOR. So you can design, you can tune your PN junction in such a way that you have the colors, the flashing colors that you can develop using those PN junction, these LEDs. Now, an LED gives non-coherent light. So that's an important point. I mean, what's the difference between coherent and non-coherent? Now, what we say is coherent means the light having same initial phase. Okay, two light sources having same initial phase or constant phase, we call them coherent. But from these LEDs, what we get non-coherent. We get non-coherent light, right? And that means the light has many phases. There are a range of phase differences that may range from 0 degree to 360 degree, right? Now, to have coherent light, what we do, we make use of laser diodes. Okay, so they are also called semiconductor lasers, and lasers. This laser light can be a visual color or invisible. These LEDs are widely used in CD players and even in laser printers and remote control devices. Now, these days, these LEDs are commonly used in optical communication. Optical communication. Okay, with this, I would like to end this talk on light emitting diodes.